Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your facilitator. We ask that you please mute your device and leave it on mute during the session. And your questions are certainly welcome. Please send them to me, Paul Donahue, via the chat feature, and we will do our best to answer them at the end of the session. Those that we don't get to will be answered as in the past through email. So I think, as you all know, these tech talks have been designed to provide straightforward insights into radio frequency components, related technologies, and the design and engineering value that's added by a custom manufacturer such as TRM. Today's tech talk is all about hybrids and couplers. People often ask why hybrids are called hybrids. Others wonder about how couplers are used in today's RF manufacturing processes. Well, to answer these and many other questions, I'm pleased to once again introduce TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles, all about passive microwave technologies, Shaun has been with the company since the late 90s. His passion for solving problems has only increased over the years, especially when it comes to helping our customers with their design and engineering challenges. So welcome, Shaun. Would you like to start by sharing your objectives for today?
Yeah, thank you, Paul. What we'd like to go over here is first define what a coupler and a hybrid is, find out, where the name came from. Hybrid is kind of a funny name. And how do we actually manufacture these parts? There's various technologies to be able to build hybrids and couplers, and go through the technology that we use to build them, and a lot of the basic math, and not going into the math, but the basic concepts mathematically, as far as to how we went from the very basic structures early on to the very broadband sort of devices that we can build today. And then we'll wrap it up with a summary and talk about TRM differentiators.
Excellent. Well, thank you. So maybe to get started here then, what exactly is a hybrid?
Yeah, a hybrid is what we refer to as a hybrid in the passive microwave industry. Is a 4-port device. There are 2 inputs and 2 outputs, so it's a 2x2 device. And hybrids are broken up into 2 categories of devices. There's what we call a 0-180 or a sum difference hybrid. In that case over there, the 2 outputs are either summed together, come out the 0 port, or the difference of those 2 outputs are coming out the delta port. Now, conversely, you can run that backwards and put power into the sum port and then have 2 equal splits on the 0 port on the 2 outputs. Or if you put your signal into the delta port, you can create 2 signals that are equal in amplitude but out of phase on the 2 outputs. Many applications that you can do that for, that you can use that for. It's a very useful circuit. The other main configuration is what we call the 90-degree hybrid. In this case over here is a fully symmetrical 4-port device. And if you put a signal into any one port will be isolated. The other 2 will split the signal, equal amplitude, and have the 2 phase relationship between those 2 outputs be 90 degrees apart from each other. So those are the 2 basic configurations that we have in the RF industry. Very flexible, very powerful as far as what can be done with them in many applications.
Okay, and I've heard you say that these networks are directional in nature. Can you explain?
Yeah, sure. So what it means is that there's isolation between the inputs and the outputs. And so therefore, if a signal is coming into one particular input or one particular port, another port will be isolated, which means the signal will not be delivered there. It'll be delivered to a specific port. That's very useful in a lot of applications. You could, for example, think of any kind of a power splitting device or directional or a coupling device as just a resistive network. If you think about it that way, energy always divides equally regardless of the direction that it's flowing in. Hybrids are directional in nature, which means that you can have you can either receive signal based on the direction of energy flow, or have the signal, or have that signal be isolated. So it becomes a very useful tool in developing higher order networks.
So what's the derivation of the name hybrid? Where did it come from?
Yeah. So in general, hybrid means taking two different functions and combining them together into a single unit. The example that you talk about now that's very popular is the hybrid car, which combines a gas engine and an electric engine. Hybrid circuits in the general electronics industry talk about combining lumped element technology into die-mounted sort of technology, or integrated circuits, where you combine the integrated circuit along with some other sorts of technology, combine them together. So that's typically what you talk about when you talk about hybrid in the electronics industry. I will say, though, that the definition of hybrid, how we use it in an RF, passive RF realm, is quite different. It has nothing to do with the fact that we're combining two different mechanical technologies of a semiconductor, along with some other sort of control components, which is how it typically is in the industry.
Is it also true, Shaun, that the name hybrid had something to do with the telephone?
It does, and that's actually where it comes back. Where it comes back to here. The word hybrid was used correctly if you think about the technology as applied to the telephone. So the telephone application of a hybrid, and this is the original derivation of the 0180 hybrid, was used for telephone networks back a long time ago. And what they did was, instead of having four wires between two telephone receivers and transmitters, you gotta remember you have two wires going to your microphone and two wires going to your earpiece back on a telephone system, and those signals have to cross across the network so that one microphone hooks to the other earpiece. And traditionally, if you go back to the original design of the phone system, you needed four wires going across the span to be able to do that. Hybrids were developed to actually take those four wires and have the functionality of a four-wire system, but by having these transformers on either end of the wire, they were able to get the same information going across two wires, and therefore cutting the number of conductors they needed in half. So this was a use of the term they combined, and by taking the function of four wires and combining it into two wires, that's where the word hybrid came from, because it still was combining, but was combining functionality, not necessarily technologies.
That's interesting. Well, how about sharing some of the basic applications?
Yeah, sure. So going back to the phone system, the original system, the original idea for this was introduced back in 1878. And basically, if you look at a couple of diagrams that are on the screen, the ones that are on the top are really the diagrams that are in the handset that allows you to get the earpiece and the microphone onto two wires without having an echo or basically having to listen to yourself while you're talking on the telephone. The same application of the same device further multiplex this down on the actual trunk line of the phone system to be able to put amplifiers on the line to be able to extend the range. So this was another very, very important development on the phone system, to actually be able to extend the range by having by splitting the two wires up as a direction, as far as signals going in one direction or the other direction. They're able to put an amplifier in line to be able to extend the range. Just fascinating technology. The fact that the idea for this happened, well over a century ago, is actually quite impressive.
Okay. And you had mentioned a 0180 hybrid. Can you explain a bit more?
Sure. So the 0180 hybrid was the original hybrid. This is the one that is based on the example in the phone system. So basically, what it does is there are two inputs, and they're isolated from each other, which means that those two inputs can operate independently. There's an equal power split between the two inputs, and basically what happens is that one of the inputs will add the differential signal coming in from the two output ports, and the other input will differentiate this signal. Therefore, you can have information flowing on those same two wires, one being in a common mode and one being in a differential mode. And by doing that, you can have information flowing in both directions over the same wire, and they won't interfere with each other. Like I mentioned before, since hybrids are directional, and that's how they become directional, is the fact that they run either in a differential mode or in a common mode or parallel mode to ground. That allows for isolation between those two signals.
So you've also used the term lumped element with respect to hybrids. What does that mean?
So the original circuit within the telephone network was a lumped element circuit. Literally, there was a transformer there that allowed for this signal to be developed. The example that's on the screen right now is a 0-180 hybrid using lumped element technology that TRM builds. And as you can see, it's just a transformer network with some compensating capacitors in it. What transformers allow is that once you have coupled energy through a transformer, by nature of the magnetic field building and collapsing, they create directional energy. So one of the basic technologies that is a direct extension from a telephone system are these lumped element 0-180 hybrids. Very popular, very broadband. Basically, these operate quite well, very broadband source of devices, and very popular as far as with various applications. They are limited to about 1 gigahertz in frequency. We have gone a little higher than 1 gigahertz in frequency in these in some devices, but because of the extraneous sort of parasitic effects that happen with the transformers and capacitors, they are limited as to their the highest frequency of operation. But they're wonderful devices that work very well.
Got it. So could you share an example possibly?
Sure. So you know, the big change here happened getting away from the lumped element technology happened back in the 1930s. Waveguide technology had just been built. And how do you build the functionality of a 0-180 hybrid into waveguide? Back in the 1930s, Barrow developed what is now referred to as the Magic T. The Magic T is a 0-180 hybrid, very similar to what was in the telephone and the lumped element part, except it applied to waveguide. So this is an ingenious mechanical device that allows that same functionality to happen in waveguide. Back in the 1930s, there were two choices if you needed to be able to have power division or power split. One is you used the telephone style lumped element. If you're trying to work at higher frequencies or higher power levels, your only other choice at that point was a waveguide Magic T. So this was very important, a critical element for the development of radar back in World War II. Because at this point, you got to remember, strip line had not yet been invented. So this was the technology of choice, and really the only technology available to us to be able to go in there and be able to build a high power divider, or a power combiner, or in fact a feed network that gave us a 0-180 kind of a phase split. So this was really a critical part that really started off a lot of the RF passive microwave industry, was the Magic T.
So what about a 90-degree or a 90 hybrid?
So 90-degree hybrids basically came on the heels of the Magic T. And what was happening is that people at that time not only needed a 3 dB split, but they wanted to sample just a little bit of power. So what a 90-degree hybrid does is it allows you to have the same isolation characteristic of a Magic T or of a 0-180 hybrid, but it allows you to be able to go in there and just sample a little bit of energy off of it. in addition to that, there's a 90-degree phase shift as opposed to the sum difference. Now, the other benefit of this, of having the 90-degree phase shift, is now the part becomes completely symmetrical, which means you can use it either for injecting signals onto another high power line, or from sampling signals. You will get the exact same symmetrical response going both ways.
Can you share some examples?
Sure. So going back to again to the waveguide technology, this was developed back in the early 1950s at MDL, and there are several different flavors of these 90-degree hybrids available. You see there are lots of different ways that accomplish having cavities leak energy into the other channel. You can either have it as a top wall hybrid, as what's shown up on the upper right. Sidewall hybrid is what's on the lower right, and those give you a nice 90-degree phase shift with equal amplitude, depending on the length of the leak of the holes that are drilled between those two cavities, and the size of those holes. You can vary the amount of energy that leaks from one cavity into the other, and by doing so, you can create a 3 dB 90-degree hybrid. The cross-guide coupler, which is on the lower left, allows for coupling at something other than 3 dB. So this one over here allows you to go in there and create a 10 dB coupler, or 20 dB coupler, or a 30 dB coupler by controlling the size of the gap or the amount of leakage that happens between those two cavities. You can actually differentiate it and not have half the energy go into that other waveguide. Just have a small portion of it go into the other waveguide. Again, very useful sort of a product, and it became really the baseline for a lot of the products that we build today from a functionality standpoint.
Now, earlier you talked about strip line and directional couplers. Can you share a few more of those details?
Sure. Strip line came out in the early 1950s, like I mentioned here. It was initially introduced in 1951 as just a transmission medium. In 1955, Seymour Cohn published a paper on shielded coupled strip transmission lines, which is the first academic treating of how to be able to build a directional coupler in strip line, and basically using the same idea of having energy leak from one conductor to the other. He proposed the mathematics that allow us to be able to calculate exactly how much energy will run from one conductor to another. This sort of technology was based on the length of line that is in physical proximity or running parallel to each other, as well as how close those conductors were, all in the same plane. This was actually one of the building blocks for this technology, but it also had quite a few limits as well. You couldn't get a really strong or true 3 dB coupling just by edge coupling strip line, but you could develop a 20 dB coupler or a 30 dB coupler using this technology, and this technology still exists today. His mathematics was based around a quarter wavelength line, as far as the length of the line that allowed at the center frequency of this coupling, which essentially gives you about an octave worth of bandwidth, which was actually for its time was revolutionary, but it really was it sort of limited the overall application. 5 years later, in 1960, Seymour Cohn again published a paper on a broadside. Again, this is a case now where you can build a 3 dB hybrid because you can have two strip lines exactly on top of each other, and he gave the mathematical solutions to be able to do that. So he gave us the ability for a edge coupled strip line as well as a broad coupled strip line to be able to calculate exactly what all those parameters were. A couple years later, Shelton published his paper on an offset coupled parallel strip, which kind of takes both of Seymour Cohn's papers and combines them and allows what happens if you have a partial overlap, or if they're separated but yet offset in the vertical axis. This actually completed the suite of what we needed to be able to do to calculate what the coupling value is for all the various configurations of strip lines. So we now have the edge coupled line, the parallel coupled line, and the offset coupled line, which really completes mathematically how we build couplers and strip line today.
That's interesting. Were there additional versions or evolutions after that?
Yes, there were. So those papers talked about individual quarter wavelength sections as far as calculating how that interaction all works. There were several papers that were written then immediately following there, where we talk about cascading individual sections. Again, from a time standpoint, 1965, 1963, it's all happening at about the same time. People are writing papers that what happens now if you use a Chebyshev polynomial to be able to cascade individual sections and create broader bandwidth structures. In addition to that, at the same time, mathematically they're developing the math to be able to calculate asymmetrical couplers and tapered lines, which allows for much broader bandwidths. These are all the basic mathematical principles, again, all coming out of the mid-60s, that allow us now to build coupled line structures that have really very broad bandwidths. Going back to the 180 coupler now, back to the Magic T sort of configuration. In taking these sort of now coupled line structures, how do we build a broadband Magic T? We still haven't had a good broadband Magic T in strip line. We have had good broadband 90-degree hybrids in strip line. So how do we do that? A very popular way to do it is the example that's up on the top of the page here, which is taking a broadband 90-degree hybrid and adding something called a Schiffman phase shifter to it. Schiffman had done his paper in 1958, giving us the mathematics for how to build a coupled structure that would have a fixed phase offset. By doing this now, what we could do is we can add an additional 90-degree phase offset to a 90-degree coupler, which then gives us the 180 phase shift that's required for the Magic T configuration. Another way of doing that is doing it as described by Duhamel and Armstrong in 1965, is to go in there and actually build a Magic T using a tapered line structure, which has the advantages now of being a full Magic T in its electrical configuration. In addition to that, this is extremely broadband function as far as the mathematics of it goes. This is it's a high pass structure, which means that it really has extremely broad bandwidths, and this is something that we use today for some of our ultra broad bandwidth 0-180 hybrids.
Okay, and what about microstrip?
Microstrip is really problematic as far as building a coupled line structure. The technology that's developed in microstrip around this has to do mostly with ring type hybrids. These are rat race hybrids, branch line hybrids, Geisel hybrids, and those are the examples that you see there on the right hand side of the page. The reason why microstrip struggles with building a hybrid or a coupler is because there is an asymmetry in the even and odd mode that's inherent in microstrip. As a result, the coupled line energy arrives at the isolated port at different points in time. Therefore, it doesn't subtract well and create very good directivity. Some things have been done over the years to help improve that over a narrow band. There are things that we do in the industry as far as capacitive reloading the coupled line structure, others like that, to help compensate for that even odd mode disparity in velocity factors. One thing that has been successful is something called the Lange coupler, which is a series of loosely coupled lines that are all hooked in parallel. This largely actually overcomes the even odd mode velocity factor by loosening the coupling on those structures. It works quite well but it only works over a very narrow band. Typically a 5 or 10% bandwidth is about all you get out of that style coupler. But that is a microstrip coupler that is used fairly extensively in a lot of narrowband applications. But really the sort of the downfall of the microstrip coupler is its bandwidth. They work quite well, and if you only need a narrow bandwidth, they're a good device.
Well, as always, Shaun, great information. Would you like to summarize?
Absolutely. So really, I think that the point of this discussion and the one that we did last month really is the fact that we stand on the shoulders of giants here. Every technical advance that we make is based on some other technical advance that happened by people that were in the industry before us. And I really think that as the prior art is developed and as we move into new spaces and new technologies, we have to reevaluate what we can do. And sometimes we have to look at what we couldn't do before and can we do it now using this new technology. It's a lot of fun. And really, I think a lot of things can be done as far as how we're actually going in and progressing this. From a manufacturing standpoint, we can look at new manufacturing processes. As computers and tools get better, we can get more accurate at predicting the results of a lot of these structures.
Okay, and how about talking about some of the differentiators TRM provides?
Sure. So what TRM likes to do is we like to work with our customers and really determine what it is that they're trying to accomplish with this particular part of the system. By going through there and be able to do that, we can find out whether or not it is a packaging requirement, whether it is an environmental requirement, or whether it's a particular place where, gee, I need a lot of isolation here, or whatever the particular parameter is. As you can see, there are lots of ways to build these sorts of devices. And really what we want to do is make sure that we pick the best way and the best approach to be able to solve those individual needs. And whether it be mechanical packaging or electrical circuit selection, that's really what we want to be able to go in and be able to do. In addition to that, TRM provides all of the environmental services and objective evidence that's required, both electrically and mechanically, to support the program. And I think I really want to stress here that TRM, we're a solution provider that provides hardware, not the other way around.
Got it. Okay. Well, we do have a few questions, and I think we have time for one. And it's a very simple question. What is the fundamental difference between a hybrid and a coupler?
At its root level, Paul, the fundamental difference has to do with the amount of energy that's coupled between the lines. A hybrid always has an equal split between the two outputs, and a coupler has a differential split. When we talk about a 10 dB coupler, for example, the through line gets most of the energy, and one port is 10 dB down. For a 20 dB coupler, the coupled port is 20 dB down, and the rest of the energy goes out the through line. For a hybrid, the power division is equal, so that the coupled port or the tap port, or whichever way you want to call it, has an equal amplitude with the through line. So it's really a matter of semantics. They are actually, from a functional standpoint, the way we design them, they're extremely similar. The main difference being a hybrid is a special case of a coupler where the power or the through power and the coupled power are equal. And whereas a coupler has a difference between the coupled energy and the through energy.
Okay, well, thanks again, Shaun, and thanks again to all of you for joining us today. If you are a customer and you have more questions, or if you'd like to discuss details with one of our engineers of any type, we'd love to hear from you. Please feel free to call our engineering hotline. The number is on your screen, 888-677-6877. There is no cost for these calls. If you're one of our field sales representatives, then you know your calls are always welcome as well. And you can also submit questions directly through the sales rep portal. In case it's helpful, our next Tech Talk will be on Wednesday, March 23rd at 11 a.m. Eastern. That topic will be to be determined. So thank you all once again. Thanks, Shaun.
Thank you.